Polyprotic acids. Polyprotic acids are acids that have more than one acidic proton to donate. And when we look at polyprotic acids, we know that the dissociation will take place in a stepwise manner. One proton will dissociate at a time. And each of those dissociation processes will have their own Ka value. So we'll have a Ka1, Ka2, and so forth. So let's say that we have the generic acid H3A. It's a triprotic acid. So in our first step, we'll remove the first hydrogen ion, and we'll have a Ka1 value for that. In the second step, we'll take the conjugate base from the first step and dissociate it and release a hydrogen ion. We'll have a separate Ka2 value for that step. And then we'll have a third step, since the conjugate base of the second step has an acidic proton. We'll go through the dissociation process there. We'll have a third Ka value. And now the conjugate base of that third step doesn't have a proton to donate, so we're done with our process. Typically, for polyprotic acids, Ka1 is bigger than Ka2, which is bigger than Ka3. And when we look at the individual steps, we can see why that is. In the first step, we're removing a proton from a neutral acid. But in the second step, we're removing a proton from a negatively charged species. And that negatively charged species is going to have a greater attraction for the positive proton, so it'll be harder to remove. And in the third step, we're removing a positive proton from a species that has a -2 charge. That species is going to be holding on to the proton more tightly, so less of it's going to dissociate. So Ka1 is bigger than Ka2, which is bigger than Ka3. So let's look at an example. It says calculate the pH and the equilibrium concentrations of oxalic acid, hydrogen oxalate, and oxalate ion, and the hydroxide ion concentration in a 1.40 molar oxalic acid solution. And it gives us our Ka1 and Ka2 values. So we'll start by identifying the major species that are in the solution, which one will be the dominant producer of hydrogen ions, and then we'll move on from there. So we have oxalic acid, which will dissociate into hydrogen ions and hydrogen oxalate ions. And we have a Ka value of 6.5 times 10 to the minus 2 for that. We've got the hydrogen oxalate ion, which will dissociate into hydrogen ions and oxalate ions. The oxalate ions don't have an acidic proton, so we're done with our diprotic acid dissociation. The second step has a Ka2 of 6.1 times 10 to the minus 5. Now we also have to remember that water is there, so we'll write that down as well, because we are going to get hydrogen ions from the water, but the Kw for that is 10 to the minus 14. So we have 10 to the minus 2 for the first step, 10 to the minus 5 for the second step, and 10 to the minus 14 for the dissociation of water. So we know we're going to start with step 1. So for step 1, we'll write our Ka expression. So we have Ka1 will equal the concentration of hydrogen ions times the concentration of hydrogen oxalate ions over the concentration of our oxalic acid. And then we'll make our ice chart. So we've got our oxalic acid, our hydrogen ion, and our hydrogen oxalate ion. For the initial concentrations, when we look at the problem, we've got 1.40 molar oxalic acid initially. And the way that the problem's worded, it doesn't say anything about having hydrogen or hydrogen oxalate initially in the solution. Our change, some of that acid will dissociate, and it will produce equal amounts of our ions. So at equilibrium, we'll have 1.40 minus x, x, and x. So now let's plug our values into our Ka1 expression. We've got 6.5 times 10 to the minus 2 equals x squared over 1.40 minus x. We'll assume that x is insignificant. Multiply both sides by 1.4. Take the square root of both sides and solve for x. Now when we do that, we're going to get x equals 0.301. Now let's do our 5% rule. We're going to take 0.301 divided by 1.40 and multiply it by 100. And when we plug that in the calculator, we're going to get 21.5%. Wow, that's much bigger than 5%. So, we've got a problem. X is significant in this particular problem. So what we're going to need to do is go back and solve using our quadratic equation. So when we take this equation up here and manipulate it, we're going to get x squared plus 0.065x minus 0.091 equals 0. Now you can either use your calculator and plug in A, B, and C into the quadratic equation in the calculator, or you can use your quadratic equation to solve for x. And we're going to get x equals 0.271 molar. And that's our hydrogen ion concentration. It doesn't happen often, but every once in a while x is a significant value, and then we have to do a little more work and solve the quadratic equation. So we found our hydrogen ion concentration. We are going to get hydrogen from the second step in the dissociation, and we are going to get hydrogen from the water, but those are going to be insignificant values. So from there, we can figure out the pH from the hydrogen ion. But let's look at the other things it asks us for. It asks us to figure out what the hydrogen oxalate ion and oxalate ion concentration is. So we're going to take that second reaction, that second dissociation, and work with that next. So we've got our hydrogen oxalate ion concentration breaking up into hydrogen ions and oxalate ions. We've got a separate Ka expression, and we're going to make our separate ice chart. So our initial concentration for our oxalic acid is going to be 0.271. That comes from this value here. The concentration of our hydrogen is going to be 0.271. And we haven't mentioned oxalate ion yet, so that'll be 0. Our change, minus x, plus x, and plus x. So at equilibrium, we'll have 0.271 minus x, 0.271 plus x, and x. Now let's write our Ka2. So Ka2 is our hydrogen ion concentration times our oxalate ion concentration over our hydrogen oxalate ion concentration. So we've got 6.1 times 10 to the minus 5 equals 0.271 plus x times x over 0.271 minus x. Again, that becomes a really complicated equation. Hopefully x will be insignificant in that second step, since our Ka2 is a smaller number. So we'll assume that this x is insignificant and this x is insignificant. And what we actually end up with is 0.271 times x over 0.271. So our 0.271s are going to cancel out. X, for the second step in a polyprotic acid dissociation, is going to equal Ka2. So x equals 6.1 times 10 to the minus 5 molar, and that's our oxalic acid concentration. Okay, so we've solved for our hydrogen ion concentration. Here, this is our hydrogen oxalate ion concentration. We've solved for our oxalate ion concentration. So now we need to figure out what our hydrogen or what our oxalic acid concentration is at equilibrium and what our pH is. So our oxalic acid concentration isn't going to be that 1.40 because x is significant. It's going to be 1.40 minus 0.271, which is going to give us 1.13 molar. And lastly, we need to figure out our pH. So our pH is going to equal the negative log of 0.271, which will give us a value of 0.567. So when we go back and double check, we wanted to find our oxalic acid concentration at equilibrium, so that's this value here. We wanted to find the hydrogen oxalate ion concentration, that's this value here. We wanted to find the oxalate ion concentration, that's this value here. We wanted to find the pH, that's this value here, and when I double check, we want to find the hydroxide ion concentration. So 1.00 times 10 to the minus 14 will equal 0.271 times x. Divide both sides by 0.271, and we're going to get our hydroxide ion concentration to be 3.69 times 10 to the minus 14. Now, a couple things that we want to point out. Make sure that if you're dealing with a concentration, you put units, molarity, 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 molarity. And also make sure you define what they are. So this is the concentration of hydrogen and hydrogen oxalate. This is the concentration of oxalate. This is the concentration of the oxalic acid. And this is the concentration of hydroxide ions. Make sure everything's clearly labeled so that all the numbers can be identified.